let's, for the moment, talk about phenomenology before we really try to offer a improved understanding of what's happening. So phenomenological behavior of phenomenology of mechanical behavior of, let's say, glassy polymers, right? That's part A of part 2. Okay. I indicated, for example, let me write it down. I know I so verbalize so much. I indicated it's brittle at room temperature. And if you make your sample properly, let's say extrude your polystyrene, very defect-free, then it turns ductile above 70 degrees C, which is still 30 degrees below its TG, which is about 100 C. Okay. And in fact, generally speaking, there is a brittle-ductile transition. So if you just blindly take your sample, you start to draw, which is tensile extension, and you record your stress in the sense of engineering stress, which is just force per original cross-sectional area as a function of drawing ratio. Then you find, as function draw ratio. Then you find that for one temperature, it's brittle like this. For a second temperature that's a little higher, it may eventually do something like this with a maximum. This is, of course, a yield point. But this is brittle. So in principle, you can plot the values of either sigma B or sigma Y as a function of temperature. You have polystyrene in mind, but this plot will be general for any glassy polymers. So you will find that this maximum is obviously the so-called yield stress. That's why we use the word sigma Y. So you have that. And then, for the sake of argument, perhaps it's much better to use a different color. Let's see, I'm running out of colors. Come on, give me. Okay. So then let's call this point sigma B. Then after some point, you no longer have a ductile behavior. The sample breaks as indicated by this is called SS curve, stress-strain relationship. So you basically get two lines. This line and that line. And if you like, of course, this line doesn't exist, this line doesn't exist. Basically, this two lines. Makes sense. So if this is the case, clearly you have witnessed a point brittle-ductile transition. Brittle on this side, ductile on this side. Yeah? This happens for all glassy polymers. For different glassy polymers, this temperature of PBD is at a different place. So for polystyrene, it could be around 70 degrees or so. For PMMA, it could be around 45 degrees or so. For polycarbonate, don't quote me, it will be something around maybe nearly a minus 80 degrees polycarbonate, which means it remains ductile until that cold temperature. And you are absolutely wish to think your polymer in your usage temperature range remains ductile, because brittle is catastrophic. It will break. Ductile, even according to this curve, means I can still bear load. Even if somehow I pass remember last time I showed you the spec, even though I passed the yield point, I know this is not glassy, but turns out that's in part B when we talk about semi-crystalline polymer. I passed the point of yield. At least I can still bear some load. That's important. Okay. How to understand this? How to understand the fact of the polymer temperature being the crucial variable that can change from one behavior to another. Answering this is very much related to what I went through with Eyring idea. Clearly, Eyring cannot deal with this transition because Eyring says, give me stress, I will lower the barrier, I will eventually have enough mobility. And it is in recognition of the fact this thing does turn brittle at some point, we realize we need something beyond Eyring. Obviously, let me give you the bottom line, at temperature low enough, somehow I was not able to activate. Unable to activate. Somehow. In other words, or you translate that, somehow the stress is not available below this temperature. So that's the point that we need to address. That's the crucial point. I wrote it as engineering stress and didn't give you a chance to explain to you what we're doing. Yes, engineering stress. Almost surely you should use engineering stress. There are two things you use engineering stress and without confusion. One, which I didn't offer the information to you, is that this breaking taking place or yielding taking place more or less around 5% or so. So in that sense, the difference between engineering stress and yield and true stress is 5%. Okay, by definition, because lambda is only 1.05. So no big deal which one you're reading. But more importantly is what I try to mention last time once, but here maybe I should just use let's see if I can find a way to tell you. So let me use this file to show you what I can further indicate for you about the nature of not only what is a ductile polymer, but why we're using engineering stress. Okay, so I'm going to address that issue right now. Engineering stress allow you to avoid, by definition, allows you to avoid plotting true stress. True stress is a senseless quantity if your drawing is not uniform anymore. You see, right? I have a section that's wider. I have a section that's narrower. The force is the same. You're dividing different areas. Then the true stress, of course, is not the same. So you cannot even plot your data with true stress. Engineering stress is different. It's merely, in your mind, you should keep thinking engineering stress is just reporting the force. Because the initial area, of course, is just a number I put in. Having said that, I'm eager to show you the phenomenology of what a ductile polymer look like with this slide. I showed you the SS curve, that's the red line. I showed you a yield point, that's here. I showed you, I didn't show you how much usually it occurs. Again, as I said, only a few percent. Let's say up to 10% when the peak, the yield stress occurs. And then it necks, as I depicted here. And then the neck front propagates. So these two movies will show you that. Let's see if I use play mode, whether it, no. You guys don't see the play mode. So this is a setting we didn't get it right. So let's play it separately. So this is one movie showing a ductile polymer, glassy polymer draw in front of an IR camera. So what the IR camera does is trying to capture the temperature. So, okay, this is repeating again. Initially it was uniformly drawing, temperature nearly constant, and that 45 degree, watch that point, is a point of yield. And it enables you to form a neck, and the neck front is propagating away from the middle that's already necked. And the propagating front achieves higher temperature because of extra plastic process going on. So that's a fancy movie. You need an IR camera to see it. But it's beautiful because it allows you to see this point. You see that point? A 45 degree failure or localization, or it turns non-uniform after that point. In a conventional camera, what you have is just this video where, let's say you want to see if it's uniform, so you mark it with something, and the neck actually already just formed here, that moment. And this neck front, here's the front. It's hard for you to see. Here's the front that's propagating downward. I don't know how well you can see, but you see that front is here. It's propagating. So it becomes thinner here, okay? And it's this necked region trying to invade into the unnecked region. See, now the spacing between them is longer now, right? Because it's shrinking, so it has to compensate by being longer. So initially, they were separated by only this much. Now it's much longer. Now it's same here. The front is right here, right now. I think the zeroth order thing to appreciate is this is magic only for polymer. It's glassy, but if I don't tell you it's a glass, you don't even know it's the glass. In the sense that it has the ability to shape change smoothly without failure. Right? So that's the notion of a ductile polymer. And you are just recording this force. So as long as this neck is still eating up to the unnecked part, the force will remain flat. If your sample is perfectly well prepared, uniform in size. And then when the neck finishes, you can have additional rise in force. in principle, which of course movie cannot tell you. It's the low cell, the transducer, force transducer that tells you. Okay. That's this ductile region. And you run out of luck as you get colder and colder. At one point, this doesn't happen. And you get this very brittle failure that you can imagine. Just suddenly it breaks. Why this happens is very much related to what I indicated last time. Why this region is unable to activate? Well, I claimed last time it's because you no longer have something to deliver the stress. As I said, this is in retrospect. This is after we figured out about the essence of what to understand here. Let's flip back. If you forget about what I said about the problem with Eyring, the problem of having to find another theory for where the stress comes from, then you realize our understanding is quite primitive. In fact, prior to my proposal about what's going on, which I will explain in more detail about, we need another theory to tell us where stress comes from. Our understanding, even up to very recently, is through this plot. I now draw the dashed line to extend this two curve beyond what you actually observe. That's because there is such a thing called LWDO hypothesis. If you want, you can go to Word's book on mechanical properties of solid polymers to find out more about what this is. But basically, I would say we kind of try to understand this brittle-ductile transition in this primitive way by assuming that somehow, magically, no matter whether your temperature is here or here, they claim that there are two competing processes going on. One is a process of breaking. The other is a process of yielding, which I'm just sort of repeating the textbook. Of course, I'm not in agreement with it. And whether a polymer is brittle or ductile just depends on this competition, which one wins. And you ask God, and God tells you the ones that give you lower stress win. Okay, so if you look at here, my red, of course, is at the lower stress than my green. So my red wins. Yield wins. Okay? And as I move colder, I claim that it actually takes more stress to yield than to break. So it breaks. Okay, I see some of you flung. Excellent if you flung. If you flung. I have very detailed criticism about this idea in a in a paper we published on crazing last year as a feature article, where I outlined in detail about how primitive this understanding is. In my view, this is nothing better than I'm asking you to go to the street, find how a cat looks like. You come back and says, it has 4 legs. Well, who doesn't know it has 4 legs? I'm asking you why its DNA give you 4 legs. Well, then of course you are not telling me why that is the case at all. So it's not very helpful. It's just a way to give up. Is it clear? What I'm restating this idea, okay? So 2 competing things, whatever has lower stress should be the one that reveals itself. You can speculate. I will have next lecture perhaps to talk more details about this. You can speculate, or I'm speculating, what's driven by, this is all detailed in this paper actually. What's driving this idea of LWDO hypothesis is the assumption that you understand what brittle failure means. It perhaps is one way of saying it. What it means is we typically assume the brittle failure occurs because of chainsation. The chains break. And that is something, if you ask people around, maybe 30% say, I believe it breaks. Another 70% says, no, there's no chain break today. But that's a part of the issue we need to address. So in any case, I'm really dramatizing it and telling you this very clear challenge of understanding why a polymer turns brittle when you lower the temperature over a rather narrow temperature range, and offers a textbook explanation for it, which is really not much at all. Well, the zeroth order thing you know is it's clearly not speaking about molecules at all, except at the end I added they may speculate the breaking is related to chainsation. You may call that molecular or not. Okay. So here's the challenge of facing you, right? All the polymers you have, the glassy polymers, that you wish it to be ductile, then you better understand why it stays ductile and when it becomes brittle. So the phenomenology, aside from this very elementary part, was really for me to show you the 2 sides of the story. In other words, what influenced this brittle ductile transition? What influences this? So as usual, before you understand why, you better know how it happened first, and by doing something that is related to what you do. So I can give you, let me see if I have it here. I can give you as I said, the phenomenology. What affects the brittle ductile transition? Okay. So just take this as sort of very useful information. What I listed 5 factors that influence this brittle-duct transition. In other words, with these 5 factors, I can turn my polymer from brittle to ductile or vice versa. So let me go one by one. There's such thing called physical aging. I very briefly mentioned about it. If you prepare your glassy state by taking more time to reach that glassy state, your glassy state tend to be older, so-called. And in addition, remember this curve. This curve. In addition, sitting at one temperature, you can make your sample more aged by annealing at that temperature. Remember that was a specific volume plot. So you can physically age it. What it does, it makes your polymer, take a note, make your polymer more brittle when you physically age it. Which make a great deal of sense because aging is a process where all your monomers are trying to settle down to a more compact state, denser state. Therefore, less mobility, therefore more difficult to gain mobility. So it's more brittle. There's another thing called pressurization. So it turns out there were several classic studies in the past. My polystyrene that's brittle at room temperature, if I hydrostatically pressurize it, my polystyrene, and then do the same experiment, they find this polystyrene turns ductile. So in all of our discussions, we are not talking about any change in chemistry. We preserve the same structure, same chemistry, just different physical means to examine which way it goes. It turns brittle, it turns ductile. So if you call this first one negative, make it more brittle. Pressure is positive, it makes it more ductile. One of the well-known one is, of course, third one, called mechanical rejuvenation. And this movie, it plays, oh Lord. Yeah, it will show that. So this is a magician's game. This is a piece of polystyrene, okay? Piece of polystyrene, it's brittle. Now you know what brittle means. And passes through 2-row mill. On the other side, it turns ductile. I know this is initially actually in a play mode is much better. So this is the illustration of it. That you basically either using twist or you pass this. Sorry about that part. You pass it through 2-row mill. It turns ductile. So the mechanical rejuvenation also make your polymer ductile. And in today's language, I group the first 3 in one category, and the last 2 in the second category. And it all has to do with how to understand polymer glasses. Yeah. Second one and third one, good point. The second one also has pressure. But it's not, look, if you look at the movie, it's not the same idea though. Meaning, when you are trying to break it, that's not under any hydrostatic pressure. Whereas the second one, it was during. You need the hydrostatic pressure the extension is done under the plate. Only then it's okay. Yeah. So I guess to appreciate this grouping of the first three involving one story, and the second group involving a different aspect, I cannot indicate that well without telling you something more elementary. Basically, what happens is we're coming all the way along from the liquid state first, and as I cool the temperature, viscosity goes up. You reach the glassy transition point. What you recognize is that, there will be a chain network in this melt state, right? So this melt state will have the chain network, and now I start to cool it. Okay, that's the screen line. I start to cool, my modulus increases from 1 megapascal to 1 gigapascal, and my network, which is in the animation on the capture, my network is of course still there. That's the network that's there. But in addition to that network, I have draw the gray dots, okay, to show that everything vitrifies, everything stuck, right? So you see this dichotomy here, or the dual nature of this, that there are two factors. One is this network. One is, in addition to the network that we're familiar with from rheology, from melt state, there is also the vitrification that give you the gray dots. And it's the gray dots that is hard to understand how they pack and give us the glassy state. I indicated last time the nature of the glass transition is still under heavy investigation. We still cannot truly appreciate its essence. But take it as it is. We know that there are two factors in our polymer glass. One is each monomer sits down and frozen. The other is that there is an underlying chain network, which we learned from rheology. So with that language, I'm indicating the first three factors: physical aging. Oh, that's just your gray dots moving closer to each other, pack better. With your pressurization, again, you're just trying to squeeze them together even better. Okay. Third one, that remember magician's game, go through the two-row mill and it turns ductile. Again, it's manipulating the gray dots around themselves to a degree. The shape change is not significant. Okay, turns out it's just some shaking at the gray dot level, at the monomer level. These first three factors obviously did not change the chain network, because there's no shape change. Okay? So this is the critical point. The polymer glass has two sides. One is what I just showed you, the nature of how they pack at the monomer level. And the other is the fact there is a chain network. In the past, we of course know there's something about this network, and we call that entanglement network. Well, that's a overused term, because the entanglement network was initially a word for for rheology. So the real question is, how do we depict this chain network in terms of its role, its function? So with that, let me come back to the slides that we went through here. So I have to look like I have to undo this, and I have to reshare. Reshare the screen. Let's see. Guys, where do I? Oh, the screen is still here. So let's reshare the screen. Share the screen to here. Okay. This away. Okay. So let's go back to here, this slide. So that's the first three factors. It's basically affecting how all the monomers are trying to pack. And that's all, the relationship is all dependent on temperature. They pack much more, in a much more frozen state if you go to lower and lower temperature, right? We know that. So here are the two factors that are very important to recognize. It turns out, I have to cut a long story short by saying it turns out actually it's known for 50, 60 years that I can make my polystyrene ductile. Remember, it's a brittle polymer at room temperature. I can make it ductile by doing the following. I go back to rheology. You take your polystyrene above TG as a melt, you draw it or melt stretch it. I mentioned something called geometric condensation. I don't know how much I will say in more detail, but basically, here's what you do. You take your polystyrene above TG, you draw it. We don't call it draw because above TG is basically a melt. We call it melt stretching it. The effect of that is that this network becomes geometrically more condensed in the cross-sectional dimension, in the dimension perpendicular to the drawing direction. So these are the two movies showing that. For example, this is polystyrene. It's brittle. You take this polystyrene, you go above TG and draw it. After drawing, you get this piece. Oops, ductile now. This has been known for by now more than 6 decades. Not only it's known, our industrial friends use this effect every day to do so-called biaxial orientational stretching to make polystyrene film. Now that polystyrene film is ductile. The question for us, of course, is why? And this is where what you learned before helps. Well, we perceive there is a network, and that network, when they calculate it, I will go through it, I don't know how much today versus any other day, next day. Went through the idea of a network have certain area density. We'll go through that next minute, I think. It has certain area density. And when I draw my melt in this affine limit, in the elastic limit, my area shrinks, but the effective strengths are still the same number. So you get geometrically condensed. As I depicted, the effective strengths are denoted in the field circles. And there are lots of open space in my cross-section because there are ones that are not effectively load-bearing because my chains folded back and forth several times. But it only has the effect of load-bearing at once. So it turns out, in short, it's the same as achieving geometric condensation. And all of a sudden, you get an object that's this instead of that. And that object simply was able to undergo yielding instead of undergo brittle failure. Okay, so a mouthful. So I said quite a bit about it, but let's go back to. Let's go back to what it does. So apparently you observe that the effect of that melt stretching is to make it more ductile. Well, keep in mind, there are two sides of the story. So if this is my original network, I draw it so that it becomes more condensed. If I establish a coordinate of z, then x is here, y is here, right-hand row, then my xy plane is condensed, as I just showed you. But if I look at the xz plane, which is this plane, for example, is it condensed or dilated? Well, it's dilated. Yeah? Because the strands are further apart, it turns out that it's trivial to realize it's dilated. It's dilated because this cross-section area during melt stretching actually become greater and greater. By how much? Because your length is increasing by lambda. Your cross-section area is decreasing by 1 over lambda. So it turns out it increases as 1 over lambda, as a square root of lambda. So the area is increasing, and you have same strength, so it's dilated. Here, in the xy direction, it's condensed because the area is shrinking as 1 over lambda. So this concept pretty straightforward, right? So you got condensed in the xy direction, you got dilated in the other dimensions. What does that mean? Well, then you can explore that. In fact, this is the tragedy of it. Or in fact, this is the reason people do biaxial stretching. So it turns out if you do it just uniaxially, you got a sample that's stronger when I draw this way and weaker when I draw it transversely. And that's true. That's true to the point that you can take a ductile polymer, you subject it to melt stretching, and then you examine it in the transverse direction, your ductile polymer become brittle. Whew. Get it? And that's not surprising. That's this data. Effect number 5. So you take your sample, you draw it this way, and then you cut your sample transversely, and that sample turns out is weaker, and it's brittle. And this movie gives you a show of what brittle means. It's just after a very little amount of stretching, it will break. breaks here. Basically, you see this has a little alignment issue, but it breaks. Okay. So if you want to depict it, basically your network becomes dilated. So let's come back to our nodes. So I have shared with you a lot of phenomenology. I listed 4 factors, essentially really just 4 factors in the sense that basically you can manipulate your network such that if it's dilated, it's worse. If it's condensed, it's better. But essentially, you are manipulating the network. Whereas the first three effects is manipulating how they are packing. So there are these 2 sides. If you just dug a little deeper, that's what they are. To connect more closely with what we talked about last time, let's put this empty suggestion with some content. So let's go back to our notes. We talked about that the Eyring idea alone would only give you ductile behavior because I always have stress. Then I always will increase my mobility. But we just learned that there are polymers that's not able to be activated, and it's brittle. And we talked about that. It means something has to be said about whether this stress is available or not. And we further says perhaps you need something to deliver that stress. Some structure to deliver that stress. And if I invoke what we draw so many times, all we know that structure is this network. And it runs through tens, millions of layers of them. If you try to think of that's the one layer. Right? Except right now, I'm not sure what is this structure, so I'm going to just give a notation called load-bearing strand instead of saying it is entanglement strand, because it turns out it's not. Some structure, some mesh size, which is yet to be determined. That's okay. I'm not, nobody should be afraid of that. But nobody should have any trouble accepting that there's some structure like this. And now I can visualize that when I draw something, remember there are this many layers between them. When I draw something, I omitted everything in between, right? When I draw something, imagine all this 100,000 million is in between this. When I draw something, well, of course I have to draw it by. Oh gosh. It's almost like saying that I draw some And I'm just leaving the rest for your imagination because they are kind of the 6 layers of them, right? What the first thing you notice, I'm teasing now, is, of course, no single chain can reach from one end to the other, right? No chain is that long. But that's okay. That's okay because we had the insight that as long as they are hooked, it will keep hooking until you hook from one side to the other. Yeah? So the whole idea is they are hooked. And they are hooked because of what you call uncrossability, or because they are long enough. Remember I told you once before, it need to be long enough to come back to itself. And once it's long enough, it will come back to itself many times. So it's very clear what is delivering the stress. It's this object. Right? It's this hooking. That enabled me to transmit the stress, to send the signal everywhere in my sample. Hey, wake up. I'm asking you to deform, to go with me. And in doing so, as I display the two ends, I am moving all the parts. And I introduce a mobility. So the premise, the new premise, meaning the way to understand this problem, is that the chain network is robust. So that it can deliver the stress. As I keep saying, if you want to preserve that language of Eyring, to me, I don't even need to preserve that language. I would simply say, if my network is intact, then I know when my ends are displacing away, everywhere is also displacing. And that's mobility. That's mobility for the backbone of the chain network. In other words, for the part that will display. You will recognize there are other parts of the chain that are not part of this network. And this is a little deeper concept that the best I can tell you is a chain is a coil. In the glassy state, if you try to displace this, obviously not all parts of the chain will display in the horizontal direction. So that's why things are difficult. Okay, this is the reality. If you think about one chain that are obviously hooked by other chains, right? I don't know how long you wish me to draw this chain, right? So could be this long, and then there's some additional chains hooked here, and this chain is trying to move, and there's you know. So basically, you use your imagination, right? It's basically a Gaussian chain. So let's say it's like this, and you may have another chain like this. Okay, let's say that's the two chain ends already. So it's complicated. You can imagine here it's being displaced a little bit because my two red chains are grabbing it to do it, and other parts are doing all kinds of things. But you can be sure not all parts of my chain is going to effectively moving in the horizontal direction. But some part will. So you will get a fraction of your network participating in this displacement, and other parts will not. So to the zeroth order, you can imagine, at least for those that can sense the fact that two ends are moving, and I'm also joining into that movement, those are the ones that, using the language of Eyring, those are the ones that will find its stress being delivered. And in other words, they experience stress or molecular force, so they start to activate. Or in my language, that portion of the chain will simply displace because it's being dragged by the two ends of my sample. So whichever way you want to think about it, there will be some partial mobility increase. As I draw more, can I succeed in causing most of these parts of my chain to go with me and to activate and to flow or plastically deform. So the premise is a very simple one, or the whole idea is a very simple one. What if the network falls apart, breaks down? But then obviously the Eyring mechanism disappears. Or my mechanism disappears too. If something falls apart, then obviously there's nothing left for that continuity, structure continuity to exist, to allow this displacement to continue throughout the sample. So just like in rheology, there will be a horse race. Perhaps somewhere something will fail. Fail through what? Well, if it's transition, fine. And if it's not transition, it can still fail by sliding. Just like we had in rheology. Now rheology. So, so you see where the issue is. You surely have a ductile region, and you surely have a brittle region. Should not draw anything more than the brittle region, and you surely have a transition. So this is either brittle stress or yield stress. We don't have anything better, but we have something more satisfying, that the chain network is intact when it's warm enough. Nothing breaks. I'm just going by kind of the simplest way to speculate what happens. And therefore, it can deliver the stress and can cause mobility to increase until it reaches the same mobility comparable to what external deformation requires that we went through last time. Or, so you may speculate, maybe the chain network breaks down on this side. Fair? You see how simple this is? At least, again, you see the power of this approach. It's called, my favorite word, phenomenological. Respect what you see. But this is infinitely more insightful than saying, no, there's a brittle process that compete with a yielding process. So we at least start to suggest it's all about whether you can succeed, whether your structure is there to do the job. And then we answer the rest of the question. Why the network fails here? We'll have to answer that question, sure. But at least, very primitively, you can speculate, gee, what's the big deal? This is, but the big deal is here, actually. Hear me clearly, this big deal. This is the biggest deal, actually, there is. You see, I introduced this so naively, so simply for you. But there's a dramatic shift in our attitude for this problem from previous understanding, which is this. What is previous understanding? Eyring. What is Eyring understanding? There is stress. It does not care what gives you that stress. In other words, to recognize that's not enough, asking us that we must worry about a structure, give us the opportunity to identify what is that structure. In other words, to explicitly say what is the role of chain network. Explicitly. Not throwing a word of entanglement, say, oh, somehow we know something has to happen for ductility to occur. In fact, indeed, we know when your ductile polycarbonate, your ductile PET is made of lower molecular weight, it won't be ductile. So we know we need a high enough molecular weight. We can even throw a word called entanglement there, but it really says little about what entanglement does. I claim here that this chain network is what enables activation. Because in its absence, there will be no molecular mobility delivered, enhanced, as my external deformation start to take place. So, so this is actually a big point, that we are answering why you have ductility. What's the answer? Why you have ductility? In fact, perhaps I can have you coming out of you now. Why we have ductility? Why a polymer can be ductile? Having said what I just said, why your polymer can be ductile? It's because it has a robust chain network. Huh? Well, that's what's said here. Oh, well, it's not quite what it said. It only said the chain network is intact. But no, it's because the chain network is the driver. How about that? Here, I want to emphasize one time and last time. We are in an environment of so-called institutionalized learning.
that you're listening to me. But you need to exert judgment in terms of whether they all make sense to you. Okay, we should not claim to have a possession of truth and a possession of knowledge or possession of understanding. I'm here presenting what I understand, period. And you can contrast that with what is available. You can contrast with what new ideas you may have, and you can reconcile with what your reasoning and logic is. But the logic is quite clear, that we need to look for a structure, and it's that structure that enabled yielding. And that structure, it seems like, is entanglement. Why? Because we went through that phenomenology. We went through the idea that people discovered in the 60s, that polystyrene, after drawing, after melt stretching, it turns ductile. Whether we understood why that is so, well, not until recent, in my opinion. Because you manipulated the chain network. We'll say more about it as we move along. But basically, if this is the case, then I call this Goldilocks temperature. It's just right. Right? You all know Goldilocks. In this, it turns out that it was quite amusing. The Europeans may not necessarily know Goldilocks table, the story, but this country, we all heard that growing up. We all heard that as a parent reading the story to the kid. So it's just right in the sense it is a temperature. Cold is no good. Hot is a different story. When it's cold, the network falls apart. When it's warmer, indeed, the network sustains and carry its mission, which is to activate. Even though you are still deeply glassy. Remember, TG is somewhere there. Okay. Questions? Yeah. Network. Right. So so if you heard I say network vitrified, you probably misheard me. Meaning the whole system vitrified. Right. So imagine what this picture says is the following. It's a melt without solvent. So every bead represents a monomer, for example. Of course, it's space filling. Therefore, I draw them as space filling. They all stuck because it's in a glassy state. Use the word, they are all vitrified. And on top of that vitrification, we recognize there's still underlying chain network, which of course is part of the whole ocean, the sea of monomers. So everything gets stuck. The savior, who is saving us, who is going to eventually allow us to get out of this misery of glassy state during deformation, is this network. Network is the Moses. It's going to bring us, it's going to take us out of the mountain. That's my premise. So this theory in counting is reaching the 7th year. Not only most people still perhaps have not heard of it, it just shows how busy we are with our own things. But those who have, perhaps more than half, are left at loss with it, in the sense they don't see why this is a necessary truth. In other words, I don't have, in fact, in response, we don't quite have the proof either. The only way almost today is maybe by computer simulation, but that still turns out to be very challenging. So, that's the glassy state is often known as a vitrified state, and you can say every monomer is a soldier. All the soldiers are falling asleep in the dormant state, and here comes the two ends. You're grabbing the two ends, and you are the general. You say, "Guys, wake up! We're marching on to the battlefield." And the soldiers fall asleep, and they couldn't hear your trumpet telling them to wake up. And that trumpet is this chain network. But if you have a sound barrier that somehow this trumpet cannot be heard when the network is falling apart, of course there's nobody who broadcasts that anymore, right? See the point? It's so elementary. Because all the soldiers need to march on for this to happen. The whole army need to go. So the miscommunication, the loss of communication is what's going to cause you to victimize, or it breaks. The end result of breaking is most of the soldiers will stay asleep, right? Basically, the sample just breaks in the middle of it. Nothing gets activated. That's a disaster. You don't want that. May use different language. It says, "Oh my God, I need some dissipative mechanism so that I can absorb the energy from the deformation." Well, that's all science fiction, because the zeroth order question is, how do I accommodate, right? How do I accommodate the fact that things are deforming on me? So, so what's left really is to try to answer the question of why there is a moment that the network would break down. That's not so different than how we may wish to visualize when we did rheology. Pretend, this is something that a formal lecture probably can never deliver it well enough. Basically, what I'm drawing when I draw like this is I'm only drawing, I may use a word, a backbone of my polymer. Well, I have to use the word with a quotation. In other words, when I extend the two ends across millions of layers in between, imagine I have some kind of sensor to measure how I start to build forces in the chain. can call it with a fancy word, intra-chain force. Imagine you do that experiment. You grab your sample, you hold it, you start to draw. Suppose I have a indicator or measurement of reading all the stress on each of the chain. What I draw here are the ones that has the force on them. We call it load-bearing strands. The total of load-bearing strands conceivably is only a fraction of the total monomer. So that's, in that sense, I say it's a black bone. So I could truly imagine that when I do this, I will see a so-called chain force that involves a network. And if I depict that network, I go back to this picture again. It's going to look like this. Or, better yet, if I look at that cross-section, I'm going to find them like this. The rest of the space are still many others that are not bearing the forces. Can you? I need you to appreciate that. It is that because your chain is a coil. Remember, there was once I told you, imagine the extreme case that your chains are chopsticks, all straightened in one direction, like this. Okay, just imagine a state where I got all my chains lined up next to each other. If I still look at, so I draw it like this. If I still look at the cross-section of XY, in that case, of course, all of them will be circles, filled circles. Am I right? And that's the concept. I know I didn't deal with the question, hey, if that's the case, how can the chain communicate between the chains? Well, let me just cheat a little bit. Let's assume I somehow have some glues between the chains, such as crystallization or something. I'm merely trying to deliver the idea that in that case, all the soldiers will wake up because before anything else, if there's no failure. So in any case, I just want you to appreciate the challenge of waking up a glassy polymer. Only the backbone is waking up, and they are the captains. They need to talk to their soldiers, wake up. So you have generals, that's at the two ends, and you have a bunch of captains that are the ones that are already got the order, got the message from the general. And so this is how it goes. And as I deform more, right? So as I deform more, the load-bearing strands will have a force that also grows more. So if you like to think, in fact, there's some tension in the chain now. So as I deform, I will build this chain tension. And until what? So the premise is I can appreciate that there will be a backbone, that that already received the message from the general that they are going to say, okay, we need to go now. As they go, remember, unlike the melt state, there's very little relaxation going on. Everything's frozen. So this actually means it's much, the force arises much more readily. The tension in the chain. Because it doesn't have a chance to relax. Don't need to speak about Weismer number. That would be too high. So, in any case, there's a game show in TV called The Weakest Link. So what is the weakest link? Well, I'm starting to touch an important point. Where is the weakest link? I'm trying to now persuade you now. Where weakest link, meaning where would be the point things will give in? Force is too much. Okay, right? I claim the weakest links are not here, here, and here. This covalent bond. Thanks God, Mother Nature gave us this carbon-carbon bond. It's quite strong. Thanks God. In fact, this part of the discussion is so amusing because I can tease you. Give you polystyrene, it's brittle. And you cry, you say, oh, I need to go back to my chemist and tell them to give me a stronger chemical bond than carbon-carbon bond. You can cry, go back and say, my God, that would require invention of an entirely new science that we don't know how to do. Carbon-carbon bond is all we have. And you go back, cry, Jesus, the only way I can improve my polystyrene is give me a new chemistry that invents a new bond that's much stronger than carbon-carbon bond. Poor guy. I mean, it turns out that's not where the problem is. Luckily, right? In that sense, luckily. So in that sense, this is no teasing. This is quite dramatic. It shifts our focus. It shifts on what are important things that dictates mechanical strength. So chemical bond takes about several, I'm just making it up, let's say 3, if not 5, if not 2, about several nanonewtons to break per bond. And there are times where you can use energy. It takes about 300 kilojoule per mole of energy to break a bond for a carbon-carbon bond. A different bond have a slight variation. Yeah, double bond, single bond. Yes. What is it? After what? So, okay. So the story is, as we're saying, I know I'm skipping a lot. As I keep drawing, this force potentially keep building. I'm asking you in this depiction, where is the weakest link? In other words, where will be a mechanism or a spot where the force will be unable to grow further? The chain tension. And I was trying to clarify, it's not coming from breaking the bond. The bonds are quite strong. So that left with only one answer, which I already revealed. Right? And it's, at least for the most part, it's not difficult to suggest that this chain may wish to pull out at some point. It's not without difficulty per se, because there are lots of surrounding monomers, and I wish I used a different color, but maybe I would choose a different color for this. So in any case, there will be, wow, it's a multicolored one. There will be a lot of friction trying to prevent the sliding, if you like. But as long as I have the vision that this chain pull-out force will always be smaller than the braking force, I know I'm being just somewhat casual, so let's just call this braking force F star. Or perhaps you like it better, just call it the braking force, FB. As long as this is true, we can imagine chain pull-out to occur instead of transition, right? By definition. So, so when you have a brittle failure, you could have some transition. The question is whether that's the dominant event or not.